Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So it's my great pleasure to welcome Ganesh Gopalakrishnan from the University of Utah to Microsoft Research. Ganesh has visited MSR many times before. He works in the area of high-performance computing, formal verification, and other related topics. Today he's going to tell us about some work that at the intersection of these two topics.
Thank you. Thank you very much, Shas, for the kind introduction, and good to see all of you for my talk. It's a great pleasure for me to be able to present some of the work that I've been doing in the area of trying to apply high performance in the area of applying formal techniques, systematic techniques for high performance computing. So I gave the initial title to be Correctness Checking Concepts and Tools for High Performance Computing. And if I really want to address the upcoming roadmap of exascale computing, I would probably offer a more pithy title, such as this is really the black ice that is waiting for people who aspire to attain exascale rates of computing. And let me say why and how we might be able to help some of those. Okay, so today's high-performance computing research is driven by the mantra of wanting to attain the maximum amount of compute per watt, whatever compute means. And we have enjoyed growth thanks to two governing laws in this area. Moore's law is familiar, which is roughly the doubling of the number of transistors. And Dennard's law has been at work also, because as and when we scale transistors, they remain rather efficient. They operated in such a way that you could pack twice the number of transistors and not exceed the thermal limits. This was thanks to the voltage scaling that was possible as and when you scale down to the lithography. But right now you cannot scale down voltage anymore. It's almost at 1 volt, and hence the CV square F hits you, and we are power capped. So Dennard's law is over, and this is from Bob Caldwell. And there are a number of worries that this induces, because if you have to enjoy the same apparently limited way of evolving in terms of computing advance, we have to be hiding several latencies in gaining performance where we were initially not able to. So never have any excess design or slack. So this is how we had to be proceeding. Yeah, but what is not being mentioned in HPC amidst all this is that HPC is also going to address very serious computational concerns and challenges going forward. So one is familiar with various kinds of industrial simulations or weather modeling. But even for surgical planning or studying the effect of introducing a stent, people are able to use fluid mechanics-based simulations to predict the wall shear. So you can do at least various experimental procedures offline. Pedestrian accident avoiding systems are going to be deployed with the assistance of GPUs, which are extremely energy efficient and mobile. So correctness is a concern, and HPC is no longer the province of big scale HPC centers, but it is coming everywhere. Yeah, so there are even verified high-performance potato chips. This is just for laughs, but Pringles apparently uses aerodynamic simulation in flying Pringles, so they shouldn't take off. So you want planes to take off, thanks to HPC. You don't want Pringles to take off, again, thanks to HPC. All right. All right. So let us see how the correctness field is in this domain. I have previously worked on cache currency protocol verification, things like DPOR and preemption variations of bounded search. And around 2003 or 2004, I started collaborating with researchers in high performance computing, just because that area was largely virgin, and yet they were writing concurrency codes pretty much on, all the time. So the real pressure or the governing force for them to operate in a certain way is get the maximum amount of science per dollar. Machines are bought and commissioned. The commissioning and bring up takes several months, and then the machine is useful for 6 years or so, and these are expensive machines. So they really have to push on that front. And many times HPC is used to explore unknown aspects of science. You are trying to predict what happens when you travel closer to relativistic speeds, or what happens inside a black hole, things like that. So you don't know what the right answer is, so you're trying to find out the right answer, i.e. cannot write assertions easily in many cases. Algorithmic approximations are made. Physics can never be modeled as such, so that is again another variability. With all the hardware performance concerns and Dennard's law being dead, we are facing the prospect of dark silicon, which means you cannot really operate all the transistors. So we really have to eke out every bit of performance, which means you need to have different kinds of CPU and GPU elements and memory subsystems. There's enormous heterogeneity. Different core types are used. When you look at number representations, you are thinking in real number space, but you are implementing floating point. And the floating point is like a noisy signal that rides over your ideal real number curve. You don't know where that noise is or where it builds up and where it affects computation. So, and precision allocation is an important consideration, because if you can compute with lower precision, you are better off doing so. There are even attempts to actually have precision in terms of storage and bring it to the chip and expand it to full precision. A lot of games available in this area. Bit flips are a worry, because bits may not be reliable. And the scientists themselves in this area are busy doing science and also catering to HPC. So Ed Lazarska, who visited our department, calls them pi men. They need to have two different strengths, and it's hard to find people who can do both well. As opposed to T-men. All right, so this is an interesting
T-men?
T-men, which is a deep single skill. Here you have to be deep in two areas. All right, this is Ed Lazarska's picture. So, all right. So here's an example of what heterogeneity might cause, and this is an actual bug story. An illustrious group at Utah has been pushing on their HPC simulations. And they recently made their code run in a symmetric mode on Xeons and Xeon Phis. So the code was working correctly in the Xeon regime, but when some of the processes were computing certain ratio in the Xeon Phi, in this case trying to send the number of messages being 162, the other side calculated the same ratio, again because of floating point round off issues, which are different. And this actually caused a deadlock. So they were wondering why the code was deadlocking. Finally, it was a floating point precision issue. So there are ramifications of this kind where continuous quantities may affect discrete decisions. And if it happens in a sequence, you may not be preserving invariants that you had in mind, because the decisions can be inconsistent. And so we don't really know the answer. They just went ahead with double precision, and it seemed to work. And when I read it further, and my colleague Zonimir questioned me, saying, why is this really happening? I initially thought it was 80-bit precision available here, 64 available here. But apparently 80-bit precision is available here. But there are subtle differences in terms of round off, and there is a safe flag that you can apply to a compiler. So these are yet to be actually tried in this area. But given the busy nature, the CS people had to be the ones coming and answering these questions. Let me talk a little bit about resilience. And finally, my talk is going to drive towards correctness issues of the familiar kind, but let me at least address some of the looming issues. If you look at some of the advanced GPUs, there are 7 billion transistors and Kepler. And if you do some math, there must be easily 10^18 transistors on a large system. And now they are all throbbing at gigahertz over a week, and at the end of that week, you get an answer. Now, what's the probability that every such transition went as planned? You can do the math and find the probability of the failure has to be so low that you get a reliable answer. So moral is that failures are occurring all the time in a system of this scale. But with HPC, the deal seems to be that the computations are additive, in the sense you are trying to compute a single number as opposed to a cloud transactional system where things might be happening in a disjoint way. So the window of vulnerability of each active computation is lower. That can have an effect. And people are actually trying to discover whether this is actually happening on some of the largest machines. So I had the luxury of seeing the Sequoia machine. I lovingly touched it and so on at Livermore, one of the which was top one recently. They are trying to run identical computations on 2 of the subsystems and trying to vote and see whether the bits are actually occurring. So verdict is yet to be fully announced, but they think it is happening. Bit flip is a loaded term. It is a multiplicity of issues. I mean, the fabricated chips don't have a single operating rate. They can be off by 30%. So which frequency do you pick to operate the chips on? You have to be guessing that. Coupled with that, hotspots. So LSB is getting bashed exponentially more than the MSB. All kinds of thermal hotspots, you can imagine. And transistors are physical objects. They wear out. And thermal stresses and cracks, they have actual pictures of how to prevent. So I'm just saying that with all this, particle strikes can make this situation worse. So it's all an additive effect. So with the scaling and the large number of parts, bit flips are a reality, which yesterday we heard Michael Carbon's talk was trying to address that in a sense. And energy is a currency. I just was at Pacific National Labs before coming here. And there is this very interesting project where they were trying to see which messages are arriving at a barrier sufficiently early. And if it happens consistently and they can learn that quickly, they just do dynamic voltage frequency scaling, which gives them 18 kilowatts of saving, which is 18 toasters. And these are highly, I mean, Exascale attained at 25 megawatts is the goal. Right now it is a gigawatt or so. So every kilowatt saved is important. So when you do these voltage and frequency games, it adds to the noise. The systems are going to be unreliable as a result. Anyway, so a few more slides and then we'll get into the meat of the talk. Power 6, they actually tried to measure bit rates. One of my former students was in the study. This is a heavily engineered machine which has all kinds of error correction. And they actually took it in E-beam facility and shot electrons on the chip, whatever, high energy particles. And then they had a very interesting triaging of where the errors are filtered. So a lot of don't cares at the circuit level, at the software level, at the application level. And finally, how many errors are marching without hanging the machine or crashing the software. That's the silent data corruption rate. And there was apparently 0.03 of the latch flips are turning into silent data corruptions, which is a very good number, very reassuring. Many of the errors are not getting through. Okay, but this is a heavily over-engineered machine, and this group subsequently wrote another paper reflecting on Power 7, and they make the remark that this hardware protecting you is not going to go on. You really need to have software-level defenses, asserts basically, and you can evaluate the asserts in a triple modular redundancy or other ways, and somehow make this whole system bulletproof, self-checking kind of thing. So this is reality now. All right, so despite all this, what are the most worrisome HPC bugs? Since many of these things are controllable and many things you don't have control over, I would really say that concurrency bugs are still a place where we can exert a lot of control. And those are going to be noticed. And some of the engineers at NVIDIA who talked to me recently or last year said that if you really have any race condition and so on, it tends to show up at larger scale. It is simply the probability builds up. So you do run into them. You cannot silently mask them away. All right, so with that, I will tell you a little bit about what we are trying to do in terms of our broad scope of research, and then try to drill into some of the specifics. So one of the most exciting projects we are involved in is called the Pruner project, which is in collaboration with Livermore. And they are basically interested in trying to identify when systems become non-reproducible. You cannot replay a behavior, and why is that? Which subsystem is acting up that way? So please help build a harness to, say, deterministically execute up to a point and then schedule around. So similar ideas as being talked about here. And Alice talked today addressed some of the controlled methods, except we had to now do it at a larger scale in the presence of multiple APIs. And so the data race detection challenges in MPI or OpenMP, MPI has message racing as opposed to data racing. Some of the failures they noticed in some of the failures at Livermore was failures at delicate ranges of sizes, and it often turned out to be a highly optimized MPI library causing it, not the user code. So again, there is no single place. So We will slowly work towards this and give them a test harness. We have a replay facility for message passing programs based on distributed execution of MPI with piggybacked Lamport clocks. We have a special version of Lamport clocks that detects a few more happens concurrently that we have engineered, and they are trying to use that as a framework to then drive other scheduling. So we will be looking at OpenMP scheduling very soon, and then we also have to isolate whether it is floating point determinism or non-determinism. So we may have to determinize the reduction operation to avoid that issue flaring up, and then see what else is causing it.
Ganesh, what do you mean by denial of service?
All right, here it was an overly optimized MPI collective which was preventing MPI point-to-points from finishing. So within the MPI ecosystem, some message types were not allowed to finish just because the other message type. Because an MPI is a runtime, you can think of all the processes impinging calls. Yeah. So some calls which had to be scheduled in a fair way were not scheduled. Okay. And so the system deadlocked, and this happened only for specific sizes. And it turned out to be a bug which the vendor corrected and all that. We are looking into floating point error estimation, which is another very nice computer science style problem. Despite the fact that IEEE has standardized floating point, it doesn't mean that there is a good understanding of when round off happens. So if you write a floating point, an expression involving floating point, David Bailey and others have shown that if you selectively assign higher precision to some of the operands and keep all the others at lower precision, it still computes fine. So a lot of analysis questions in this area. And again, the floating point error that I mentioned earlier. So people tend to slap double precision, but double precision costs you double the bandwidth, at least for GPUs. So you can't really afford to be indiscriminate in terms of precision allocation. So we have a search-based lower bound determining. So we run two modules, one being the native precision, one being an exaggerated precision. Try to walk through the input space in a basically delta debugging or genetic search way, seeing where the outputs deviate. So that gives you a good estimate of lower bound. That we had a PPOP paper this year on that. And for the upper bounding, which Alexei is working on, we have several abstraction techniques. Interval arithmetic, affine arithmetic, they're all valuable methods, but sometimes they don't track dependencies of variables. So we are trying to come up with much tighter bounds. So we can then see whether the bounds agree, in which case we are getting a reasonable estimate. System resilience wise, we are beginning to work on that. We have developed an LLVM level fault injector, and there is some collaboration with Shuendu Lahiri going on here with Zoramir. Okay, so let me now turn the attention to HPC and concurrency itself. And the real problem with concurrency, now I'm setting aside all the other issues and looking at the concurrency bugs, is the explosion of the number of APIs. This is not all of them needs to be present in a given setting, but many of them are. And each API sort of thinks that it owns the machine, which is a resource issue. I'm not getting into it, but it's looming in the horizon. We don't know how the runtimes interact. But the real worry, which I will illustrate with some examples, is that everyday programmers are exposed to low-level concurrency in some cases. And this is not the desired path in the concurrency space, because we thought that the Joe programmer didn't need to know about low-level concurrency, but apparently that's not too true. Yeah. So then I will talk a little bit about that, and then go on to other aspects of concurrency. Okay, so I thought I will also give some sense of reality to the talk, realism to the talk. So I will quickly demonstrate two tools, even though it's coming out of context, because I don't want to interrupt the talk later. So I'll give you a feel for, all said and done, what do our current solutions look like, and then we will come to the more slide-oriented. So I'll be talking about correctness checking of GPU programs, and we have a tool called GKLEE. I'll run that for a few minutes. And then we have a dynamic checker for MPI programs. So I'll be talking about GKLEE, which is which has been which evolved out of CLE. We just engineered CLE to understand a different memory organization, which is unlike GPUs. So if I were to present, in the benefit of people who are watching, if I were to present symbolic execution, I could even start with binary search, and then it puts the assumes and searches for a symbolic item. And if the item is found, it prints a star. If it is to the low side, it prints an L, prints a high item, it prints an H. So I can now compile it with LLVM, and then that's different. So it's running symbolic execution, and it found 11 ways to execute the program. It has generated 11 inputs. So you can sort of look at this, and so H not found means it went through the H 3 times, the high path. L not found, that it found that path. It found that. LHH. So you get the idea. So this is what symbolic execution does. It does input generation and drives the program. This is the Dart and Smart kind of technology, engineered and well implemented in GKLEE. So the point I'm making is good sequential symbolic analysis is going to be central to us, and in fact we will turn the GPU verification problem into a sequentialized examination of the schedule. So that's how that technology is going to play out. So let's run some GPU programs just since we are here. So if I were to run this GPU kernel, and the syntax is kind of not entirely CUDA in this version, but we have caught up with CUDA. So here this main program will call a single kernel called race, and this kernel will be run by the given number of threads, which I'm not mentioning here. But it's easy to see that if two threads with 0 and 1 are run, thread 0 will be writing location 0, reading location 1, and thread 1 will be writing location 1, reading location 2. So there's a race. So we are going to schedule in a manner that I'll explain soon, but the bottom line is that it actually finds a race, and you can drill into the LLVM, and that's where the race is and all that. And to give you a feel for how well this might work on a CUDA kernel, which is a radix sort implementation. Again, I won't explain what it does or how the problem might be, but if at least it'll give you a sense of time it takes for a tool like this. This is the first implementation of GKLEE, and I'll be talking about a few others. So it found a race, and you can drill in and identify that it is a race between thread 0 and thread 4, and then you let you scratch your head and look at the input and find out where it raised and how. Okay. So that's enough for this demo. What else is possible in the space of message passing programs? And this is not symbolic analysis, this is dynamic analysis. So let me again run a quick demo of this illustration. Now here the students put in a lot more effort, and we have engineered an Eclipse integration. We hope to have that available. But again, to give you a feel for what we might do, here's a message passing program written in the MPI style, and we want to find out if there are issues here. So here's rank 0, rank 1, and rank 2 code. So rank 0 means process 0, which is going to send a non-blocking send a message to process 1. Rank 1 process 1 is going to have a wildcard receive, any source means anywhere, then a specific receive, and then rank 2 is going to do a normal send. Okay, so let's see how we can test it. We can do MPI CC, this is how you compile it, and then the standard, then you MPI run. No problem, this code seems to test fine. Okay, sometimes you get lucky. Okay, didn't get lucky. Whereas our replay debugger applies a different compilation, ISPCC, which is a little bit different way to compile. And if I run it now under ISP, it actually finds out if there are dependencies, and then so it actually replayed the code twice, and then in the second run it found a problem, and then I can spawn a user interface, and then it tells you there are two ways of running the program, where in process 0 this was a non-blocking send which was picked up by this non-blocking receive. There was this barrier, And then somebody put the send after the barrier, thinking that this send is forced to be matched here. But if you now go to the second interleaving, that's not the case. There was a racing communication, because once this non-blocking calls reach the barrier, they can cross it, and that enables this other send also to pop up its head, and it is an eligible matcher. So this is we actually schedule based on an underlying happens before graph, and so we have a happens before a theory of MPI. We know how to schedule it.
So this is a deadlock because the send on the left
Yeah.
cannot have a receiver now because it's got to hit a barrier.
Well, in this case, this receive, which is a specific receive, got orphaned. It wants another message from source 2, but there is no more message to offer.
I see.
Yeah.
So really the send from 1 should have been received by the receive from 2.
That's right.
Okay.
Yeah. So this was the intended match. Yeah. So at least this gives us a feel for the kind of tools that we have built. But let's now go on with the main line of the talk. And feel free to ask questions at any point. So I have. All right. So now let us dig in and try to revisit the GPU space. And let's start from the beginning and look at how a user experiences concurrency and what errors they might be subject to, just because they don't understand or the documentation is not clear. All right, so to remind you of GPU programming, GPUs are a model of computation where you have a memory hierarchy of threads accessing shared memory, and then global memory. Barriers can be used within this, and so if you want to do a summation of an array with AI plus B, you deploy multiple threads. The details are not important. It's a SIMT model, single instruction multiple thread, and typically threads are batched and scheduled. Okay, so here's one piece of code that is contrived, but it illustrates a certain point, because many people tend to assume that since there is this warp business, meaning a bunch of threads, in this case 32 threads are scheduled as a batch, this single instruction is going to finish before any thread engages in this execution, and hence there is no need to put anything here. Okay, and so when you run this, compile and run this, the expected answer shows up, because each location is initialized to I, so it would have been 0, 2, 4, 6, 8 when you do this addition, except this thread, this instruction came in, and ith thread wrote in the I plus first location a flag value, so it killed those values. So that's the right answer, fine. Okay, so as soon as you apply optimization, you're getting a different answer. Okay, so these are issues that are widely discussed in CUDA forums. So I'm just saying things that really tend to trouble users are at this level, well before we come into races and all that. Okay, so what's going on here? We had to ask the NVIDIA compiler expert, and he said that the warp programming style is discouraged, and compilers really understand the warp to be of size 1. So really, you must think as if this is asynchronously interleaving with the threads being able to interleave in any way. There is no guarantee that this will be entirely done. So that's this. And we had dug into the code to see why this is happening and all that. So so no guarantees provided. Okay, so the real reason why this happened was this value was held in a register, and this value was computed, but then the register updated. So it's bad code. There's no. So the recommended practice is to slap a volatile. So this is another thing that sort of illustrates how this area works in terms of published documentation and what the users are. So what are C volatiles? This is going back to the C volatiles, which is a technology device for device programming those days when C had to respond to commands in the manner described. What does it have to do with concurrency? There is no clear answer. The concurrency semantics of C and C11 memory model has no mention of C volatiles. It is going the C11 atomics and all that. So the side effect that you're getting is the values are no longer held in a register. But that's giving you this benefit, and hence everybody's happy and going away. So there has to be some user education and retraining. And the worst thing is that if you really track the documentation chain that is going on in this area, the volatile practice was recommended as practice in an earlier version of CUDA. The volatile practice has not been mentioned in this version of the CUDA manual, and it's not clear what's going on. So the point here is there are errors of a low, I wouldn't say grade, but of a user education documentation nature that really are important in this area. This is a fast-moving area with many things happening, and the users cannot be expected to keep up.
It's so unsatisfactory because in older versions of the document,
Yep.
it explicitly encouraged this warp style of programming, saying
Yes.
if you want to get high performance,
Yes.
you do not need to insert barriers, and it gave an example.
Yes.
And then,
Yes.
from what
Yep.
you told me, there
Yep.
was a phase where they said,
Yep.
the compiler might do something strange unless you slap a volatile.
Yes.
And now they've just removed any mention of it. They haven't said
it's
this is now just
Yeah.
like, it's just
Yeah.
gone. So
Right.
it's not like now it says this is deprecated. It's just disappeared.
No. I'm not. Yeah.
Orwellian.
Sorry.
Said it's Orwellian.
Orwellian.
Yeah, I'm not entirely willing to. I mean, this is computer science has seen this before. I mean, if you go back to the 70s or early 80s, MC68000 came in the picture, and it couldn't do page fault handling at the last location of a segment, and MMUs came because they were new. You know, when new things happen in hardware, people really have struggled with a lot of these breakages. So I really would attribute that to growth pain and just things being happening so fast. Yeah. And they are open to engage with us. So Ali and I have some engagements with the OpenCL and NVIDIA teams, and we need to work on formalizing these. But if you look at the threads, these are all issues, threads talking about this issue that I mentioned. And here is a user's lament. I wrote this piece of code, supposed to work under the warp semantics, but it doesn't work unless I slap a sync threads, in this case, a big hammer, okay, which is a barrier. So that's safe, though. So anyway, so I won't go on this tangent for a long, except to say that we've been also, some of our students have been diligently looking at things out there. There is an actual textbook with a published example of reduction, and it doesn't work. And we have actually demonstrated it doesn't work. We have talked to NVIDIA experts. So I can get into the details later. So the basic idea is that in different thread blocks, thread 0 was responsible for accumulating, doing the reduction unto itself, which is fine. Now, having acquired values in thread 0, they were all engaging in an atomic add into a global variable. There they assumed memory visibility, so that the atomics have a fen semantics, and it doesn't. So you can actually be picking up a stale value. So this is so these are the levels of trouble that arise. I mean, this is in a book, so why would people not use it? There is a work stealing queue in GPU gems, which we have broken, and we are documenting the error. We haven't contacted the authors. But again, this is a store issue where the two stores were assumed to happen in that order. We need a fence between them. So there aren't that many of these, but these need to be captured and thoroughly documented. And people are relying on this happening reliably, especially in very ambitious GPU codes where ghost zones are used, multiple overlapping ghost cells, and then they compute locally. And but they really need a fen semantics there. Yeah, so CS has a role to play. This is just a little interlude. We need to build some cool showpieces. So we built a cool showpiece, and we are planning to teach a concurrency course based on it. So this is our little Raspberry Pi cluster. We actually, since we are getting up to teaching HPC and giving hands-on, we asked the students, some of my two good students, gave them a $500 blank check. Basically, they bought the Raspberry Pi. It runs MPI, so some. It's fun. We can run the. I can show you offline. I can do the core temperature and then run MPI matrix multiply. It runs like a late 90s Linux machine each core, and then look at the core temperature again, put the fan and all that. Yeah. All right. So I have looked at the basics of GPUs, and now let me get more into the more serious aspects of GPU debugging. So having gotten past the first order errors, where do we go next? So this is a project where Ali and I and Shaz have inspired each other and published many papers with similar thrusts. And the tool that we have is called GKLEE, like I said before. So let me get a little bit into its operation. So we can take advantage of the fact that for much of what the programmers write, GPU program is largely a sync thread barrier where threads are all aligned. They all compute in their own private spaces or private portions of the global memory and then synchronize again. So the general idea is that a CUDA program can be thought of in this abstraction as sync, run some read writes, control flow, whatever, but shown as linear sequences. So this is a very embarrassingly parallel situation. So you don't need to run all possible interleavings here, i.e. all these executions are equivalent. So if this is the only conflicting pair, let us say, this is a read, this is a write for the same address, and let us say every other read and write are falling into different locations, then you don't need to run all these schedules to discover this race. It's the DPOR to the extreme. You can actually run a single canonical schedule. This is also going back to Saridadve's days of 1990, where you can sort of run this thread sequentially and then record every access in that sequential run, and then at the end of the run you call the SMT solver to see if there is any overlapping access that you can solve. If so, there is a race. So this is the style of race checking that we implemented initially. And of course, let's also see. I mean, this of course didn't scale that well, so we are coming to better techniques. The reason this doesn't scale is obvious, because if you are given a 200,000 CUDA program, the execution length is pretty long, and there's so much symmetry there. Why are we doing all that? So we will come to that. But let's even look at an actual CUDA program to see what races might there be in this CUDA program. So obviously this is a waiting race when threads 0 and 1 or 1 and 2 are colliding. But then the barrier, and then there is for all the even threads do a read, and for all the odd threads do a write involving that. Okay, well, this is a conditional, so either this happens or that happens. Is that true? Well, that's where we need to be a bit careful about what conditional it is. It is a conditional on the threads divergence. So either all the odd threads execute first, then the even threads, or vice versa, and the order is unspecified. So there is a race there. So you do have a classical race, and then there is a unordered situation of whether you do a read or a write along divergent warps. So this is.
You're assuming there's only one warp here.
This is assuming one warp in this case. Yeah. And this is not mentioned anywhere in CUDA documentation, so we gave it a name called porting race. So if you port it for a different platform, you might find a different behavior kind of thing. So we are looking for both races, kinds of races, in a sense. Yeah.
But if you assume a warp size of 1.
Oh yeah. Then yeah.
This is an ego full stop. Right?
That's right. Yeah.
Okay.
So I guess.
So this is still if you're kind of accepting.
Yeah, but still, the fact that it is getting sequentialized in a certain way may give somebody the comfort that results are looking deterministic, even though you have a conflicting access across the N and the L. So the caution there is if you were to run it to a different platform where the write happens before a read, the results will change kind of thing. Yeah, so this is like different arguments of a C function call being unordered. There is a possible race, same thing. So we actually do canonical schedule in this way of this kind. So just to give you a point. So we are going to run 2 threads and or as many threads as there are, and then we notice the accessing pairs across them. That's what SMT will solve. Okay, so that was the original tool in PPOP 12, and we built an LLVM based flow. And then, as I said, the concrete witnesses are a nice handy feature of these tools. They tell you where the error is, which threads, and all that. Okay, so the next improvement was to try and avoid having to examine all the threads concretely. How about if we look at how threads are diverging based on their IDs? Okay, so that's the next nugget of an idea. So imagine a contrived program where you have decoding based on block ID of threads, and then thread ID, and then block ID. So what we have is a situation where all the threads come into a point where some of them flow this way, others flow this way, and then they are splitting lanes. So we have symmetry in each flow group. That's the observation. So within each flow group, like here, the threads are executing essentially identical code. So what we do in an actual implementation is to model basically we run one symbolic thread and then make a clone of it and give it another TID, which is different from the original guy's TID. So we are running 2 symbolic threads per flow group. And that is possible in a symbolic executor. You don't need to get concrete IDs. You can pretty much run these flows. Go ahead.
So I'd really like to understand this.
Absolutely.
I don't get this business of whether you have one or
Okay.
two per flow group.
Yes.
So, which is it? Is it?
It is in actual implementation. He may have my student may have taken a choice which I don't understand. But let us say that we are, in principle, let us say that we have an assume TID different from TID prime,
Okay.
and then we are executing each
So
flow.
at the beginning of execution, you have one flow.
Yeah.
You have two arbitrary threads with different
Arbitrary
IDs.
threads with
And now you
different
come across
IDs.
this condition,
Yes.
and you may ask the constraint solver,
Yeah.
is there only one solution? In which case they will both go the same way. But if it's possible for them to go different ways, you now
Yes.
end with 4 threads, right?
That's right. So each time
You
there will be an
say-
assume of that condition, assume of that condition.
Okay, so you see these 4
Yes.
threads all have distinct IDs,
Yes,
and in this flow,
Yes.
their IDs are even,
Right.
and in this flow, their IDs are odd.
that's right.
Okay, and then
Yes. And that will be part of the assumed on that execution part. So the way CLEE models it is modeling LLVM level constraints. So for each LLVM load and store, it is an SSA kind of constraint. So it's equality between new and old. And for each conditional, it is a path constraint.
So once you pass
Yeah.
one of these divergent conditionals,
Yes.
you split, and with
Yes.
your initial work, there's like no return from splitting.
Initial?
With this initial work,
Yeah.
there's like once you've split into 2 flows,
Yeah.
that's it. There's no way back.
There's
on
no way
this-
back
on
here.
this trace.
That's right. Yeah. So for this example itself, we will be generating several race checking conditions. We don't do safety assertions here because we don't have full assertions. We are assuming that a world where we are not given an input condition or intermediate assertions. And we are boiling, so far we have focused on data race checking for this tool. So if I were to lift the skeleton of the flow, what we will be generating would be verification conditions for race checking, which amount to recording all the accesses in this flow, and under that condition, which is the flow condition and the TIDs being different, is it possible to solve there being an overlap between conflicting pairs in that flow? And we do that for every intraflow, and then we do interflow also, just because, like I said, in the divergent warp, you don't know the scheduling order between the odds and evens. So we do checking across also.
Some kind of independence of addresses on data or something like that. So, I mean, you want to look for
Yeah.
a race by looking at some finite number of threads.
Yes.
So I'm assuming that the thread that I read at is not dependent on some value I read that was
Yes.
written by some other thread that we're not.
We haven't written a theorem, to be honest. So I think it is possible to write a proof that if you have an actual assertion for the starting state of the system. So let me make an example. A reduction kernel sort of works like a logarithmic tree. So each thread adds to its neighbor, and then it adds 2 away, and then 4 away, and so on. So after you do that, the behavior, the value of thread 0 is going to depend on all the locations of the array, and things like that.
That a given thread is reading or writing.
That's right.
So
Yeah.
and it's the addresses that determine the races.
That's true. That's true.
Right.
So if you did a prefix sum,
Yeah.
and then it's quite common to do a prefix sum and then write to an index which is
Yes.
like A or B of I, where
Right.
B is the prefix sum.
That's right. Yeah.
Okay.
So long as
So
it flows into a sensitive spot, which is in this case an address access, that becomes germane. The value that you compute, which turns into an address, becomes germane. Yes.
Right. So then,
Yes.
let's say, so basically, if I understand it, it's
Yes.
as if you have here,
Mhm.
you know, some set of concrete threads,
Yes.
and a bunch of the rest are abstract threads. Right. So the concrete threads are parameterized by their IDs.
The concrete threads basically gives you a range for the whole thread population, and what
so
we
you have
execute.
some representative threads. But
Yes.
Now,
Mhm.
if I read some data out
Yes.
of memory and
Right.
then use that as an index,
Right.
you know, or as an address,
Yes.
right? Then that value may have been written by some other thread.
Absolutely.
It's not modeled here. So
Not
in
yeah.
that case, do we report a race or not report a race?
In this case, there is a very interesting thing going on. You cannot be reading and then using that value, and we are going to do this check per barrier interval. So within each barrier interval, you basically cannot have any communication between threads. Yeah, so we are going to be just picking up the values and then incorporating in whatever value you have in the final state.
So then you
But when you want to build information across threads, you had to sort of be crossing.
All right, I think I remember that.
Barriers.
I'll start with this, but
Yeah.
So then at barrier,
Yes.
you may need some kind of an annotation.
That's right.
An invariant.
Yeah.
That you have to write. So is that something that's user?
Well, in this case, since we are computing, this is a computational framework. The invariant is basically the strongest invariant. We basically are computing forward. I don't know whether you need a more relaxed invariant than in.
But how do you compute this? That means you have to be able to compute strongest post for an
Okay.
arbitrary number of threads.
Right.
For a parameterized system.
Right.
So you do that.
Why I'm wondering, related
Yeah.
to Ian's question, is suppose you have this simple example.
Hmm?
A thread does A
Hmm?
at TID
Yeah.
becomes equal to TID.
Okay.
Okay, and then there's a barrier.
Okay.
So this would not introduce a new flow, if I understood correctly.
A of TID equal to TID.
There's no control flow here. Just a single statement. A of TID becomes equal to TID.
Yeah, that's an interesting point. Depending on, I think you have to basically fork. I have to, I don't know whether it is happening in the current system, but that assertion can be satisfied or not by different instances of TID, right? If for a given starting content of the array.
I mean, my idea would be you write your TID to TID of A, then you synchronize, okay? And then you say B of A of TID plus 1 becomes equal to 42.
I see.
Okay? Now this would be data race free by construction because A is populated in all different ways.
They are different. That's the invariant.
So GPU verify would not be able to prove this kernel correct. You'd have to use what we call a barrier invariant to make this work.
Okay.
And I mean, when I was reading your paper, I was trying to understand whether GKLEE, I understand GKLEE would have no problem because it has all the
GKLEE
threads.
computes, yes.
So what I was trying to understand with GKLEE, do you have this approximation of the shared state?
I have, as I told you, we are yet to write up a full formal account of this work, but I believe that if you have a full assertion covering the entire set of state variables, what we are doing is computing for 2 proxy threads, but if you were to expand these 2 proxy threads for all the TIDs present in every flow, you have the power to determine the full extent of the states that you get at the barrier. And then you will be solving a specific starting initial state. You are not covering for the full generality of the code. But given an initial state, you are computing essentially all the symbolic next states for every location.
So
and then the usage of the array cannot, let's not get into too many details here, but I do understand the concerns here. But the usage of the calculated value as you expressed in the example happens in a subsequent phase, I guess, because if you have a data race in this interim, we would have reported and found it. But the usual race-free usages of calculated values happen after the barrier. So let me think about that, and we need to drill into a little bit more and analyze.
Seems like maybe you could do a very compact execution from one variable to the next.
Yes.
Then if you wanted precise information, you'd have to do quite an expensive assumption across all concretizations of that.
Concretizations. Yeah, I'm yet to write a proof, but I haven't really found, I guess the work is yet to be taken to that level.
Okay.
Yeah. Yeah. So what we are doing actually, the completeness theorem would be interesting to write, saying that if there is a race, under what conditions this guarantees. That's something that the student who is finishing up soon has to write up. But I don't see why this should be an issue because we are again starting from an assertion, and I'll leave it at that. Okay. I'll come to a related story which is under construction again. This is assuming that there isn't, let us say, a usage that breaks the address use, breaks symmetry. For many examples, we were able to find all the races that we had found before. But there is another issue lurking here, which is what we addressed initially. So you might have this flow division happen in a loop. So we are back to exponentiality again, because if one flow has to build up enough knowledge for the next flow. So we have experimented with doing LLVM static analysis to see how much information flows from one barrier interval to the next. And the flow is being calculated for the sensitive spots, which are precisely the address spots. So we are able to take the flows in one barrier interval And we do a forward analysis to see whether some of the values computed under the different flow conditions flows into the address or the conditionals. And if that doesn't happen, we are doing a big OR of them. So for any flow that doesn't feed forward, we are basically building an OR constraint and going with a single flow. So this technique is valuable. That's the most definitive result, barring since we don't have a theorem at hand, is that this is tremendously valuable. And we have covered several of the benchmarks that we couldn't handle before, and we have gone after several of the larger benchmarks, the Lone Star benchmark from UT, which is a pretty serious set of GPU benchmarks, Parboil from UIC. And yeah, this explosion goes away for several classes of examples. So if you look at Bytonic sort, this was one example where it exploded. But if you look at this structure of the Bytonic sort, the values that you compute, because each thread decides where the location would be at the end of one barrier interval, where the data. And then, so these actions that certain threads will have to take in the next barrier interval depend on other threads' actions in the previous barrier interval. But there is no flow into the address position itself. So we were able to collapse the flow. So there seems to be the basis to formalize that. All right, so I would say this is the story for GPU verification as far as the tool goes. The tools exist, and the student is wrapping up, and we'll discuss the related details when we come to his dissertation. The nice thing with an execution-based framework is also that we are able to detect unexpected traces, which is a valuable thing. So if you have several programs where out-of-bounds accesses happen, we are able to, thanks to the symbolic execution, find those cases which occurs. All right. What I'm planning to focus on now in the remaining part of the talk is how we are able to take some of the formal ideas and maybe try and apply it to larger scale. So this is just one project which has gone this way, but what it has allowed us is to situate ourselves in the context of a large scale project going on at Utah. So the project itself has been going on for a decade now, and they're building a multi-physics simulation framework. And it's a very structured computational framework with 1 million lines of code in it, and a pretty serious effort over several PhD students. And they have achieved scalability of this code base on national leadership machines. So let me tell you a little bit about how the system is architected, and tell you the one technique we have tried which has gained some traction, and see how we might take that forward. So the system itself is designed around a nice partitioning of concerns, where the designer writes the computational intent in C++ as a task graph of sequential activities. So they largely write sequential functions, and they express dependencies. And this might be various force calculations and other temperature, whatever, pressure calculations, and how they are to be orchestrated. And then the infrastructure takes on this task graph and then executes it in a maximally parallel way. It has a scheduler that understands how to schedule these and arranges for all the message passing, MPI messages and all that. And the system architecture, just to give you a glimpse of what the scheduler contains, it's a fairly interesting system. We rely on the designers of the system to give us a handle on understanding it. So the main part of this was the experience of seeing something designed to a large extent. They have a data warehouse, which is a distributed hash table that parks the data. They have various task graph nodes being evaluated in a node. There will be replicas of this evaluation engine elsewhere, split over a large system. And then when there are data dependencies, there are messages that are being waited on. The overview, what I would like to convey is that this is a system that they have engineered to have GPUs and Xeon fees, very smoothly extended the system. What can we do, and how complex are these? These are all the examples of fast-moving HPC frameworks that groups develop to get science done. And we had this 2-year involvement with the postdoc. So a lot of what we tried to do was to understand the system. Then we said, okay, they have documented failures, so how about trying to find a cheap way to diff two versions, and that may be a good bug root causing facility that we can give them. So by two versions, I mean if they have a scheduler, in some cases they had an older scheduler, when they migrated to a different scheduler, something broke. So we want to identify where the fault was and help them isolate it. In some cases, two different inputs may have caused the system to behave differently. Or in some cases, there might have been a latent non-determinism where they observe something. So when I say diff, it would be diff across any of these variations. So the idea is kind of very similar, and in fact, Tom Ball and Jim Laris have worked on similar graph structures. They call it some call path graphs and things like that long ago. A lot of these call graphs methods that are around, and we devised a particular version of it, and the name that we give it is a coalesced stack trace graphs, or coalesced path graphs. What it is a control flow summary of the system. So how did the control reach a particular point? And the usage modality is that the user identifies where the system broke and picks a certain function call as having as being the vantage point of interest. So in this case, it's a data warehouse put. So then the system recording is turned on for, say, one scheduler, and then that records all the calls that start from the system initialization and goes through different function calls. And each node here represents a call from a certain calling context of the parent. And then we develop these big fat lines that tells you how many of this function's call reach this function, and things like that. So this is a summary of how many calls went through various functions starting from the top and reached a particular point. And what we basically do is record it over two versions and then find a diff. And all we can say at this point is it has helped inform the designer, and we have 4 or 5 compiled examples of how this brought us very close to being able to debug further. So this is a facility where the user interacts and might use printfs, might use a debugger, but this brings you closer with less effort. So the formalization of this, I don't know what to say. It is just a quick way to X-ray it, and we have seen that this is something that you can turn on without too much overhead. So what we do is we don't deploy it at 1,000 million cores or anything. In fact, in a real instance, we take the full code base and populate this, do this instrumentation for 3-4 processes. And this code is available also. You can actually slap collect calls in any sequential or parallel program. It records the things. And we even found an uninitialized variable case this way by recording over 2 different frames of time. There was one instance where we found extra call going through one way, and we had to then use a debugger, and then there was a surprising value that sort of indicates some garbage sitting there, and so this is all right. So it really is an interesting eye-opener for us, because we want to help these kinds of users, and we thought, what is the next step? So the real eye-opener is that these systems, so this is a big picture graph, and I'm almost done. This is trying to envisage how we might make some of these large-scale systems observable. So not only do we want these systems and the subsystems to be verified and assembled together and push a button, but we really need a hierarchy of observers in any such system. We can't really run these systems open loop. So i.e. automata. There seems to be ways to infer the protocols existing at various interfaces, and then it's also clear that these automatons cannot be at 1 grain of time, because and we cannot use some of these automata at the lowest level. If you put an automaton to observe the actions of a non-blocking data structure, well, you're going to lose all your performance. So we had to sort of situate these automata at a medium event size, and then because actions here span several orders of magnitude in time, from nanoseconds to milliseconds. So we may have to define a hierarchy of these observed automatas, and then the way we have tried to use automaton learning for selected modules. So we did passive learning on the data warehouse. We have some examples of automatons being able to be inferred. So The positive signatures are the observed behaviors. The negatives are, well, the user has to write assertion saying these causalities are there, and we try to use some SAT-based automated learning methods. So I think this is really a good way to imagine building a large-scale system where you have the ability to actively test and observe, and then if a fault occurs, there must be a quick way to summarize the fault, maybe using a stack trace graph or something like that. So hopefully if this idea flies, I'll get some money in a few months. Otherwise, this is NSF proposal having to be submitted again. All right, this is proposal where, okay, yeah. With that, I think I'm done. So correctness in HPC has a different ring to it, and it has been an interesting experience. We are really going forward in some specific areas. I think the main pet projects are floating point correctness. That's a real attention gripper for us because we think we can get somewhere with that. System resilience, there's some effort, and GPU verification, we really want to push forward and get some tighter guarantees and also release the tools. And finally, the need for user training and community involvement is also clear. So with that, I will wind down and take any questions. Yeah. Right. Go ahead.
So there's been, people thinking about the bring up problem in hardware, for example, where something goes wrong in the lab and you're trying to reconstruct somehow the trace of what happened in the hardware, even though you couldn't observe it, and you have, among other things, this problem of what do you want to record, given that you have a limited ability to record a trace at runtime. So I would suppose that the same kind of problem occurs in HPC, in a big computation, where obviously you can't trace everything. So are there ways that you can get at this and try to infer, what is the what do you need to know to reconstruct, one of these graphs that you have of a useful trace of execution?
Right. Yeah, well, we had to limit our ambitions, like Shas always says, and we had to sort of attack smaller problems to get more control. So just even imagining textbook variety MPA programs where the user does all the rank division and lets the processors do something. Yeah, we could record some of the salient events where dependencies happen. So wildcard receives non-deterministic probes. Rest will all play out deterministically. So there is a minimal recording possible.
Right.
Micro checkpoints are possible depending on the MPA system. But as soon as you cross, now you have two things, MPA and OpenMP. Okay. Yeah, things start getting ugly.
Well, you have a bigger problem, I guess, because in hardware, in bring up, you have an observability problem.
Yes.
But usually, if something's going wrong, it's going wrong after a fairly small amount of time.
Yeah.
Right. So maybe some billions of cycles, but still it's pretty fast. And so you can do a lot of replay trying to hit something.
That's true. Alan Who's backpace work is a very interesting example.
You can afford to do a lot of replay. But here you can't. Because you had some gigantic computation that ran overnight or something. So it seems like you have in a way, a much larger problem.
It is. I think the real hope is this system, Uinta, is very, very beautifully architected, and there are other examples of that, the Charm++ system and so on. They have an architecture which reduces these task graphs according to causality. So there may be some events that you can record at this level. So it gives you at least an initial control skeleton of where things happened, and they are not, these can be recorded in a distributed way.
Are the architects interested in questions of determinism and replay and so forth? Is that on their radar?
Yeah, this is an interesting reality check question because they also have the same problem as formal methods researchers. They had to graduate students and then look for the next student to continue the research, and they had to meet certain other objectives, like they had to solve the next physics problem or the next new machine. So I think this area has this feeding frenzy. If there's a new machine, it makes all the sense in the world to jump onto the new machine, just because you run 5 times faster with less energy, and then that's where things break also. So, but all said and done, we are working in this controlled way of writing NSF proposals, and if this gets funded, we will have that person. Yes, yeah. And the other thing is this task graph framework is so nice that you can make some of these tasks checker tasks. And the nice thing is then it can use the load balancer. It can run on an idle core automatically. So the framework is well engineered to stick in some of these checker tasks along with the regular. So I really, I'm very enthusiastic as soon as wrote this, had this experience and wrote this proposal. We think that this vision is not bad. This is the right, because there are so many ways you can get queues. Task graph reduction gives you partial order. This has a well-architected scheduler flow, the scheduler queues, So the design intent is clear from many, many facets. So if we can somehow intersect them and put the right minimal observers, so that might be a good way to replay up to that point. And then these systems also checkpoint after every millisecond seconds. It takes a system checkpoint, although that's not going to be affordable in the long run. Yeah, apparently when I went to Sequoia Machine to Livermore, apparently they have this maintenance days. 6 days a week they compute, and one day, whatever, the AC has to be fixed. It's a huge facility. So all jobs get checkpointed, but at a coarse frequency, but this needs more than that. Yeah. Well, thanks for all the questions, and again, thanks for the opportunity. Yes, and I'll follow up.